and welcome to today's Friday Math Happy Hour. Today we're going to be covering sets, probabilities, permutations, and combinations. Okay, these are the topics again. The first topic we're going to cover is introduction to probabilities, and I believe that's where we left off last week. Basic concepts of probabilities, multiplication principles, permutations, and combinations. Okay, this is a section from 8.2. Random experiment, which is a process by which we observe something uncertain. After the experiment, the results of the random experiment is known. And the sample space, denoted by S, is a set of all possible outcomes of a random experiment. Examples. For example, say that we flip a coin, right? The sample space can either be heads or tails, right? Which is the sample space will be H stands for heads and T stands for tails. So that'll be my set. The sample space of rolling a fair die. A fair die is a six-sided figure that has a 1, a 2, a 3, a 4, a 5, and a 6 on each of the sides. So our sample space will be 6, 1 through 6. Okay, now, to find the sample space of an experiment, at times it is easier to draw a tree diagram. Example, find the sample space of flipping a coin twice. Okay, here we go, right? This is my first flip. It either can be a heads or a tails. That's my first flip or my first toss. My second flip or my second toss, if it's heads first, then it can be heads or tails. If my first toss was tails, then it can be tails, heads, or tails, tails. So here's my sample space. It can be HH, which stands for heads, heads, or it can be HT, which stands for heads, tails, or it can be tails, heads, TH, or tails, tails, TT. So this is my sample space. Heads, 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 tails, tails, heads, and tails, tails, which we got them from here. Okay, now, an event. An event is an outcome or set of outcomes of a random experiment. Example. An event is a subset of a sample space. Here's the example. If a sample space for flipping a coin is a sample space, which is S equals to HT, then one event, say that what's the event of being a heads, so it will just be the set with the heads inside, which represents the outcome of heads. Checkpoint. Suppose a die is tossed. Write the given events in set notation. The number showing is less than 3. Remember, my sample space is a set of 1, 2, 3, 4, 5, 6. So the number showing is less than 3 is going to be the set of 1 and 2. Okay. Now for B part, the number showing is a 5. Well, it'll be the set with just a 5 in there, and that's it. For C part, the number showing is 8. The set will be an empty set, or the set with nothing in there. Why? Because there's no 8 in the sample space. For D part, the number showing is even. Okay, the even numbers between 1 and 6 is going to be 2, 4, and 6. That's my event. Now comes the basic probabilities, the basic probability principle. It says let S be a sample space of equally likely outcomes, and let event E be a subset of S. Then the probability that the event E occurs is, this is P of E. It equals to the number of the event over the number of the sample space. Okay, example. By this definition, the probability of an event is a number that indicates the relative likelihood of the event. Okay, and like I said earlier, the N of E is the number of elements in the event, and N of S is the number of elements in the sample space. Checkpoint. Suppose a single fair die is rolled with a sample space S equals to 1, 2, 3, 4, 5, 6. Here's the probability of each of the following events. Okay, now guys, let me clarify something here. A fair die means that a die that it's because at times they use loaded dice. To cheat when they roll a die, right? If it's loaded, it's going to go to one particular number where the heaviest weight is. So a fair die means that all the sides are the same weight. This way, it's fair. That's what it means by a fair die. Okay, now let's start with A then. The event E. The die shows an even number. Recall, guys, the sample space is 6, right? An even number will be 2, 4, 6, which will be 3. So N of E is 3 and N of S is 6. So the event of an even number is the event of the number that are even over the number of the sample space will be 3 over 6, which is equal to 1/2. Now for B part, the die shows a number less than 10. So number less than 10 is going to be all the numbers in the set, 1, 2, 3, 4, 5, 6. Which means N of E of the event is 6 and the sample space is 6, so over 6, which is equal to 1, or 100%. The die shows an 8, right? There's no 8 in the set, so it'll be 0 over 8. 0 over 6, my bad. 0 over 6, but the answer is 0, because there's no 8 in the set from 1, 2, 3, 4, 5, 6. So the answer will just be 0. Okay, now, checkpoint. Okay, we're doing the same concept here. It says here, a single playing card is drawn at random from an ordinary 52 card deck. Find the probability of drawing a queen. Okay, now, I asked my class this if they know how to play cards. And I was surprised that more than half the class, they don't know, they never seen cards before. Or maybe some have seen them, but they haven't really played. So when I was growing up, we all play cards. So people like over 30, they know what cards are. So this is for the young folks, okay, for the young students. I'm gonna have our pictures here of the cards. Okay, a single playing card is drawn at random from an ordinary 52 card deck. There's 54 cards in a deck because there's 2 jokers, but the jokers don't count. Okay, they're like, wow. So here they only say 52. And here are the cards. You see, these are called the clubs. They go from an ace all the way to a king. These are called the spades, the suit of spades, from ace all the way to a king. This is called the suit of hearts. It goes from an ace all the way to a king. And this is called the diamonds, the suit of diamonds, which is an ace all the way to a king. In other words, there's a 52. There's 13 on each suit. 13 clubs, 13 spades, 13 hearts, and 13 diamonds, a total of 52. Okay, now if you notice, there's 26 black cards and 26 red cards. Also, hey guys, what are face cards? Face cards are the cards that have a face. For example, the jack, the queen, the king, they have a face, so these are called face cards. If you notice, there's 3 face cards for each suit. Okay? Okay, now, so here's a probability. Okay, so let's start with A. Okay, the probability of drawing a queen. We know that there's 52, the sample space is 52. So there's 4 queens, right? Because there's 4 queens, because there's 1 queen from each suit. A queen of clubs, a queen of spades, a queen of hearts, a queen of diamonds. So it's 4. It'll be 4 over 52. Then you reduce it to 1 over 13. So this is a probability, 1 of 13. For B part, the probability of drawing a diamond. If we notice what I mentioned earlier, there's 13 diamonds. So it'll be 13 over 52, which is my sample space, and then we reduce it, so it's going to be 1/4. Okay. For C, a red card. Again, I mentioned earlier that there's 26 black cards and 26 red cards. So a red card is going to be 26 over 52, which will be 1/2. Okay, and finally, for D part, it says a face card or an ace. Right? So, hey guys, how many face cards are there? There's 3 for each suit. So there's 3, 6, 9, 12. So there's 12 face cards. Right? But it says here, or an ace. How many aces do we have? We have 4 aces, right? The ace of diamonds, the ace of hearts, the ace of spades, and the ace of clubs. So it will be 12 plus 4 over the sample space, which is 52. The result will be 16 over 52. When we reduce it, it'll be 4 over 13. So these are there's a probability that you're going to draw a face card or an ace, 4 over 13. Now, on the homework, guys, there's a whole bunch of these, similar to what I just explained. But with this, you'll be able to do some of the homework. Pertaining to this topic here. Now, this is 8.3, basic concepts of probabilities. Okay, this is called the addition rule for probabilities. It says the probability of E union F equals to the probability of E plus the probability of F minus the probability of E intersects F. Okay, let me show you how this formula is used. And this example comes straight from the textbook. It says, when playing American roulette, the croupier or the attendant spins a marble that lands in one of the 38 slots in the revolving turntable. The slots are numbered 1 through 36, with 2 additional slots labeled 0 and 00 that are painted green. You see, here they are painted green. This is supposed to be half, okay? I made a mistake here instead of white. Half of the remaining slots are colored red and half are black. In roulette, the slots labeled 0 or 00 are not considered as even nor odd. Find the probability that the marble will land on a red or an even. Okay. Solution. So let the set of red be R. Okay, so we're going to call the set of red BR. Right, so these are the ones that are red. And we notice I already did all the work for you here, guys. For example, you see we have a 1, we have a 3, we have a 5, right, and so forth. I already did that for you guys. And I got that from the roulette table. Now, let's let the set of even be E, because it stands for even, right? So how many are even? Here are the ones that are even. I went around the turntable and I got all the even numbers, right? For example, where's my 2 at? The 2 is right here at the bottom. 2, 4, 6, right, and so forth. So they're all here. Now, here's my formula. Because we want a red or an even, so this is a formula we use. This is a probability that red or even equals to the probability of R, which is red, plus the probability of E, which is even, minus the probability of R and E, which means where do they intersect. Okay, so here we go. Total, right? There's 38 total slots. There's 18 red and 18 black. There's 18 even and 18 odd. So the red and even, right? So we want red and even. So what we do here, guys, we're gonna get where they intersect. You see, this means red intersects E, what they have in common. So if we go here, right, which ones are red and even? There's 1, the 12, the 14, the 16, the 18. That's 4. The 30, 32, 34, 36. That's where they intersect. So it's 8 total. So we're looking for red or even, right? So that's my formula. So how many are red? Will be 18, right? Because there's 18 red and 18 black. So it'll be 18 over 38. How many are even? It'll be 18 also over 38 because there's 18 even. Minus, where does a red and the even intersect? Which was here, right? Which was the 8, right? The red and even are the 12, the 14, the 16, the 18, the 30, 32, 34, 36. So it's 8. So it's going to be minus 8 over 38. Right, so now if we do this, guys, when we add them, 18 plus 18 will be 36. 36 minus 8 will give us 28. So the answer will be 28 over 38, and we can reduce it to 14 over 19. This is the answer, guys. Okay. And that's how we use this type of formula. I think it's called the addition rule of probabilities. Now, let's do something similar pertaining to this section here. It says, suppose two fair dice are rolled. Find each of the given probabilities. Okay, so let's draw, right, so again, this is, the same formula as before. Let A represent the event. Let A represent the event that the first die shows a 2, right? Because that's what they want here. The first die shows a 2. And let B represent the event that the sum is 6 or 7, right? Which is the second part. So here are all the combinations that the dice can be rolled. If you notice, for example, it can be a 1-1, it can be a 1-2, and right and so forth, because it's a pair of dice. So if you notice, there's 6 across and 6 down. So 6 times 6 is 36. So my sample space will be 36. Okay, now let's do the event A. It says let A represent the event. The event A, the first die shows a 2, right? So this one here, guys, in red is event A, right? Because the first die is a 2, right? All across here. So event A is going to give us 6 because there's 1, 2, 3, 4, 5, 6. So event A is 6. Now event B, the sum is 6 or 7, which is shaded in blue. Right, it's going to give us 11, right? Because we have 5-1, 4-2, 3-3, 2-4, and 1-5, which is equal to 6. The sum is 6. We have the 6-1, the 5-2, the 4-3, 3-4, 2-5, and 1-6, which is the sum is 7. If we add those two sums, it's going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's going to be 11. So here's my formula, right? So my P of A is 6 over 36. My P of B will be 11 over 36. Now, what we're missing is where both of the sets intersect. If you notice, they intersect here with a 2-4 and a 2-5. See, there's 1, right? The 2-4, the 2-5, so it's going to be 2. So it's going to be minus 2 over 36. So 6 plus 11 is 17. 17 minus 2 will give us 15. So the answer will be 15 over 36. And this can be reduced to 5/12. So the answer will be 5/12. Okay, now, let's do part B. The sum is 11, or the second die shows a 5. So the sum is 11. Right here, guys, okay? Let me show you a way that you can read this. If we notice, as it diagonally, for example, 1, 1 will give me a 2. You see, and then 3 will be these two here, the 3. Then comes a 4. Then the sum is equal to 5, and so forth, right? So if you go diagonally, it'll be the sum of 5, 6, 7, 8, 9, 10, 11, all the way to 12. For example, the 11 will be right here. These two here, the 5, 6, and the 6, 5. But anyway, again, there's 36 on the sample space. There's my formula. So let A represent the event, the sum is 11, right? And 11 is right here, the 5, 6, and the 6, 5. So it's going to be 2. And let B be the event that the second die shows a 5. The second dice of 5 will be here where the 5 is across, right? The second dice of 5, so it'll be all these right here in blue. So it's going to be 1, 2, 3, 4, 5, 6. And it'll be a 6. Now, where do they intersect? What do they have in common, right? It's going to be right there. It's only one of them. So it'll be 1. Let's put into the formula. 2 over 36 plus 6 over 36 minus 1 over 36 will give us 7 over 36. That's your result. Now, with these two examples, you'll be able to do most of your homework. Okay, because there's some in the homework that are a little bit more challenging, but at least you can do the ones that are kind of basic. Okay, now this is called the complement rule for any event, which means the probability of E complement is equal to 1 minus the probability of E. And P of E of the event is equal to 1 minus the probability of the complement. Because the complement means not. Okay, that's what it means. Now, odds in favor of an event is going to be the probability of the event over the probability of not the event, or the complement of the event. Observation, right? P of E is equal to N of E over N of S. And P complement of E is equal to N complement of E over N of S. Right? So this becomes N of E over N of S times the second fraction. You flip it, and it becomes multiplication. So it'll be N of S over N of S over N of complement of E. If you notice, N of S over N of S is equal to 1. So that's where they get the formula from. N of E over it'll be the number of E over the number of not E. That means for the odds in favor. Okay, now, this is actually from the homework. It says here, a marble is drawn from a box containing 3 yellow marbles, 4 white marbles, and 8 blue marbles. Find the odds in favor in drawing a given marble. Okay, a yellow marble. So, because it's talking about odds in favor, it's going to be odds in favor in drawing a yellow will be yellow over not yellow. That's what the formula means. So how many yellow are there? There's 3. Over not yellow will be the white and the blue, which is 12. 3 over 12, you can reduce it to 1/4, but this is how you write the odds in favor. That means 1 to 4. For example, when you gamble and all that stuff in Vegas, that's how they have the odds. Like 1, I think it's a colon 4. That's I mean the correct answer, 1 to 4. For B, odds in favor of drawing a blue marble. So it'll be blue over not blue. How many are blue? There's 8 blues. And 7 not blue. So it'll be 8 to 7. Those are the odds in favor. For C, odds in favor in drawing a white marble, so it's going to be white over not white. So there's 4 whites, and there's 11 that are not white. So the answer will be 4 to 11. That's how we do these type of problems. Okay, now, it says here, this is from number 47. I believe, guys, these here are from the older edition. But these are in the book, but maybe the numbers might be a little bit different, but this is from the previous edition. Okay, now, it says here, data from the 2016 General Social Survey can allow us to estimate how many hours people who classify their work status as part-time or full-time actually worked in the last week. Use the following table to find the probabilities of the events. So for 47, right, it's going to be the probability of E over the number of E over N of S. So here, guys, the number of full-time workers, but first of all, right, this is my sample space, 15 over 91. The number of full-time workers, let's go here, full-time workers will be 1271. Right, that's my sample space. And full-time workers will be 1271, right, because it doesn't, they don't specify if it's a full-time worker working all these hours. It just says full-time worker, so we go full-time worker all the way across will give us 1271. So what we're looking for will be 1271 over 1591. It's going to give us something like approximately 0.7989. That's your result. They want you to round off to 4 places. For 48, a part-time worker, right? So we should know that the sample space is 1591, and the part-time workers here, right, will be 320. So it'll be 320 over 1591. So approximately 0.2011 is your result. Number 49. Worked 50 hours or more, right? So 50 hours or more will be 393, right? Because these are the 50 hours or more. 393. So the probability of the work 50 hours or more will be 393 over 1591, which results into 0.2470. Number 50, worked between 0 to 19 hours. So it's here on the first column, which will give us 106. So the probability that the worker worked 0 to 19 hours will be 106 over 1591, which will give us approximately 0.0666. Now, right, so again, this is a formula, guys. Now, let's do that in my sample space. Number 51. It says a part-time worker and someone who worked 40 hours or less. Remember, guys, the word and means intersection, and the word or means union, okay? And that, I explained it when we were covering sets. So let's do this, right? The word and. So part-time workers will be, this is my part-time workers. Let's see part-time workers and work 40 hours or more. So it'll be 49 plus 21 over 5091. Because 40 hours or more is a 40 hours to 49 and 50 or more, right? Because it just says 40 hours or more, so it'll be these two here, the 49 and 21. We add them up. It's going to give us 70 over 5091. So approximately 0.0440 is your result. Now I'll do 54, right? So that way you guys can do 52 and 53. 54 says or, right? The key word is or. So it attempts its wise to use this formula because it will be easier to see. So the P of E, right? Here's how we got this, right? It's going to be 320. Why 320? Okay, this is part-time worker. So part-time worker is 320. That's where 320 comes from. Or someone who worked 40 hours or more, or more. No, 54, or work for 29 hours or less. So 29 hours or less will be these two here, which will be 106 and 129. Okay? Then minus the 77 and 87, because these, they already counted here, so I don't count them again. So this is where they intersect. Right? Or if we want, we can do it this other way. I think this will be much easier to see. Okay, here we go. Let A represent the part-time workers, and let B represent the ones that work 20 hours or less. Okay, so here we go, right? So N of A, how many are part-time workers? Will be the 320, right? The ones that work 29 hours or less will be 106 and 129. You see here from the bottom, from 0 to 19 hours is 106, and 20 to 29 hours is 129. Minus, right, where they intersect. Where does A and B intersect? Where do the part-time workers and the ones that work 20 hours or less intersect? You see it'll be right here, minus these two here. That's where they got the formula from. So it'll be 391. So it'll be 391 over 5091. So the answer will be approximately 0.2458 is your result. Now comes this is 9.2. These are the multiplication principles, permutation and combinations. But this, the first topic will be, for this section will be multiplication principles. Here's like the definition. Suppose n choices must be made, with m1 ways to make the first choice, m2 ways to make the second choice, and ... all the way until you pick all the choices. Then there are m1 times m2 times m3 times m all the way until you have the choices, so you multiply them. I know that this definition is a little bit hard to understand at first, but perhaps with an example, everything will be clear. Okay, this is 24 from page 477. It says how different heating cooling units are possible if a homeowner has 3 choices for the efficiency ratings of the furnace, 3 options for the fan speed, and 6 options for the air condenser. Okay. So use the multiplication principle. So the number of choices for efficiency ratings, right? So the number of choices is going to be 3. The number of choices for fan speed, let's see, fan speed is going to be 3. And the number of choices of air condenser will be 6. So by using the principle, it will be 3 times 6, which will give us 54. So there's 54 ways you can actually select select the items under this situation here. Now, more examples pertaining to this topic here. It says, the United Postal Service currently uses 5-digit zip codes in most areas. How many zip codes are possible if there are no, that's supposed to be no restrictions, not restrictions. Okay, it's misspelled. No restrictions on the digits used. How many will be possible if the first number could not be a 0? So here, guys, this is 2 parts. So for the first part, right, we should know that the 10 digits make all the numbers because we start from 0 all the way to 9. And here's, right, no restriction on the 5-digit zip code. So how many can go first, right? How many can go on the first lot? It's going to be 10. How many can go the second? 10 and 10 and 10 and 10 because there's no restriction. So you multiply those out, so it'll be 100,000. 100,000 possible ways. For the second part, it says the first number cannot be a 0. So this one cannot be a 0, right? So this cannot be a 0, but it can be a 1, it can be a 2, it can be all the way to 9. So the answer will be 9. Because it can be 1, 2, 3, 4, 5, 6, 7, 8, 9, but not a 0. And then 10, 10, 10, and 10. Because the only restriction was that the first number cannot be a 0. That's why this is 9 times 10 times 10 times 10 times 10, which will give us 90,000. Now here's another example. For many years, the state of California used 3 letters followed by 3 digits on its automobile license plates. Okay, notice 26 letters are in the alphabet, and 10 digits make all the numbers. So how many different license plates are possible? Right, so there's here, so there's 3 digits. So my first 3 are digits, are letters, and my second 3 are digits. So how many letters can go on the first lot? 26, 26, and 26, because there's no restriction. On the second one, 10, 10, and 10. You multiply them out, you're going to get something like 17,576,000. Part B, when the state ran out of new numbers, the order was reversed to 3 digits followed by 3 letters. How many new license plate number were then possible? So all you do is flip the order. So the first 3 are going to be digits, and the second 3 are going to be letters. So again, no restriction. So it'll be 10 times 10 times 10, 26 times 26 times 26. The answer will be the same as part A. 17,576,000. Now for part C. Several years ago, the number described in part B were also used up. The state then issued plates with 1 letter followed by 3 digits and then 3 letters. So what they did here, guys, they started with 1 letter, they added 1 letter, right? And that was it. You're going to be surprised how many license plates are possible with this arrangement just by adding 1 single letter. Right, there's my letter that they added. Let me go back. There's my letter. Those are my digits. And the other letters. So it'll be 26, 10 times 10 times 10, 26 times 26 times 26. Multiply them out. It's going to give you 456,976,000. If you notice, guys, it went up by like almost 440 million just by adding 1 letter. And I believe, guys, that's the way they did it when cars were barely built. Every car had a license plate. So the more cars that were built, the more letters they had to add, or digits, because every automobile has to have a different license plate. I mean, this is for each state. Now comes the topic of factorial. Factorial means for any natural number n. If you start with n factorial is equal to n minus 1, n minus 2, until you get to 3, 2, and 1. Okay, it's multiplication, but let me show you an example so you know what I'm talking about. And by definition, 0 factorial is equal to 1. Checkpoint. A, right? So what's 4 factorial? By applying the principle, it'll be 4 times 3 times 2 times 1. Multiply them out. The answer is 24. For B part, what's 6 factorial? It'll be 6 times 5 times 4 times 3 times 2 times 1. You multiply them out, and you get 720. For C part, what's 1 factorial? Will just be 1. For D part, what's 6 factorial divided by 4 factorial? Okay, 6 factorial will be 6 times 5 times 4 times 3 times 2 times 1. And the 4 factorial will be 4 times 3 times 2 times 1. You notice these are going to be 1 divided by 1 is 1. There'll be 1. There'll be 1, and there'll be 1, right? So we have only 6 times 5, which will give us 30. So the answer is 30. Now comes permutations. Okay, a permutation of a set of elements is an ordering of elements. For instance, there's 6 permutations in ordering of the letters A, B, and C. For example, it can be ABC, ACB, BAC, BCA, CAB, and CBA. So there's 6 different arrangements by the order of 3 letters. For the permutations, the order matters. For example, ABC and CBA are 2 different orders. Okay, that's why there's going to be 6. The order matters. Example number 3. How many batting orders are possible for a 9-person baseball team? Solution. There are 9 possible choices for the first batter, 8 possible choices for the second batter, 7 possible choices for the third one, and so on until we get until 1 choice for the 9th batter. Right? So it's going to be 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1, which will give us 362,180. Or you can do it by using the factorial, which will be 9 factorial, which will be the same thing. These two are the same thing, right? Because 9 factorial is the same thing as 9 times 8 times 7 all the way to 1. Now comes another way of permutation, right? This is if NPR, where R is less than N, is the number of permutations of n elements taken at R at a time. Then the formula NPR is equal to N factorial over parentheses N minus R plus parentheses factorial. Here, guys, the order matters. Okay, example. I have 3 letters A, B, and C. I would like to know how many 2-letter arrangements are possible. Okay, remember the order matters. I like to use an example because we can actually see it. If we use more than 3, it's going to be hard to see because we might leave out one of the orders, one of the arrangement or the orders. So so we have to from the 3 letters we have to take 2 at a time. So it can be AB or it can be BA, right? Because here, guys, the order matters. That's why it can be AB and BA. It can be AC or it can be CA. And finally, it can be BC or CB. So there's 6 possible arrangements. Okay, now how do we use this formula? Okay, here's how. There's 3 letters total, and you want to arrange them in 2s. So N is a number of elements or orders, right? I mean of letters. So it'll be 3 permutation 2. Which would be 3 factorial over 3 minus 2 factorial. There will be 3 factorial over 1 factorial, which will be 3 times 2 times 1 divided by 1, which will give us 6. That's where this comes from. This is also, you can put it into the calculator, guys, but at times it's good to know how to do it by hand. And if a calculator is permitted, well, then use your calculator. Right? Or you can do it this way, right? So you have 3 letters and you want to arrange arrangements in 2. So you're going to put 2 slots. There can be 3 in the first one and 2 in the second one. The answer is 6. At times, guys, this is easier to understand here instead of the formula, but it's up to you. Okay, number 40 on page 478. from a cooler with 8 cans of different 8 cans of different kinds of sodas. 3 are selected for 3 people. And how many ways can this be done, right? So I'm going to do it both ways, by permutation or by doing it this way, guys, where you put 2 slots, where you put a slot for each choice. So first, let's do it by the formula of permutations. So there's 8 total sodas, right? And you want to get 3 for 3 people. So it's going to be 8 permutation 3, which will be 8 factorial divided by parentheses 8 minus 3 factorial. 8 minus 3 close parentheses factorial, which will give us 8 factorial over 5 factorial. It will be 8 times 7 times 6 times 5 factorial. The factorials cancels. So the answer will be 8 times 7 times 6, which will be 336. Or you can do it this way, right? By putting a blank for each choice. So here, guys, right? We have three different people, right? To select 3 sodas for 3 different people. So it's going to be 1, 2, 3, right? 1, 2, 3. So how many can be selected first? It's going to be 8, right? 8 different types of sodas. Say there was a 7-Up, Coke, Pepsi, Sprite, whatever, right? Up to 8. Root beer, whatever it is, right? Say that the first choice, right? There's only 8 of them, but they're all different. Say that the first choice, they chose a Pepsi, right? But you can choose 8 of them for the first choice, right? Say there was a Pepsi, right? So how many are left? It's going to be 7, because a Pepsi cannot be drawn again because it's already gone. Right, so it's going to be 8 times 7 times 6. You see, guys, if you notice, it's what we have here on the formula for the permutation. 8 times 7 times 6. And I believe at times, guys, I tell my students that they can do it either or. What makes sense better for them. And the answer will be 336. Now comes combination. Combination, which means the order does not matter. Okay, let's do the same example as we did earlier with the permutations, right? But now we have the same 3 letters, A, B, and C, and we would like to know how many 2-letter groups are possible. Remember, order does not matter. So it can be AB, it can be AC, and it can be BC. That's it. The answer is 3. Why? Because AB and BA is the same thing, right? Because order does not matter. So the answer is 3. 3 possible groups. Okay, now how do we put into the formula? It's going to be 3 combination 2, which will be 3 factorial, right, by following the formula, over 2 factorial times 3 minus 2 factorial, right? So it's going to give us 3 factorial over 2 factorial times 1 factorial, which results in 3 times 2 times 1. And the 2 factorial is 2 times 1, and the 1 factorial will just be 1. So here, guys, right, the 2's cancels, the 1 cancels, so it will be 3 over 1. The answer will be 3. Okay, and remember, the order does not matter. This is number 46 from page 478. It says 4 items are to be randomly selected from the first 25 on an assembly line in order to determine the defect rate. How many different samples of 4 items can be chosen? Okay, so it's going to be 25 combination 4, right? So it's going to be 25 factorial over 4 factorial over 21 factorial. It's going to give us 25 times 24 times 23 times 22, right? We stop at 21 factorial because we have at the bottom 21 factorial. So those are going to cancel. We know that 4 times 3 times 2, right, is equal to 24. So the answer will be 25 times 23 times 22, which will give us 12,650. That's your result. Now here's the summation. To sum it up, on permutations, these are the 2 words: arrangement, schedule, order, and other matters are the key words. For combinations, the 2 words is group, committee, set, sample, and order does not matter. Here's how you can tell which ones, what are they asking for. Okay, now, number 59 on page 478. A lottery game requires that you pick 6 different, I forgot to put here numbers, 6 different numbers from 1 to 99. If you pick all 6 winning numbers, you win $4 million. How many ways are there to choose 6 numbers if the order is not important? So this, guys, the order is not important. It's going to be a combination. Okay. So it's going to be what? It's going to be 99 combination 6. The answer will be what? 1,120,529,256. Now for part B, right? Order, the number of order, the order matters, which means permutation. So it's going to be 99 permutation 6, which will give us 806,781,064,320. We notice when the order matters, it's going to be a lot more than when the order does not matter. Number 60. In exercise 59, you pick 5 out of 6 numbers correctly, you win 5,000. In how many ways can you pick exactly 5 out of 6 winning numbers without regards to order? So it's going to be combination. Five out of 6 will be 6 combination 5. Okay, but remember the lottery requires that you need to pick 6 numbers from 99. So this is because 5 plus 1 is 6, and 6 plus 93 will give us 99. So it will be times 93 combination 1. Right? There's a 99 and there's my 6. So if we do 6 combination 5, it's going to give us 6, and 93 combination 1 will give us 93. So 6 times 93 will give us 558. That's your answer. Now, I believe this is the last problem for this workshop. It says a financial advisor offers 8 mutual funds in the high risk category, 7 in the moderate risk category, and 10 in the low risk category. An investor decides to invest in 3 high risk, 3 high risk funds, 4 moderate risk funds, 3 low risk funds. How many ways can the investor do this? Okay, so here we go. Solution. If you read the problem carefully, order does not matter. So order does not matter is going to be combination because the order does not matter. So from the 8 high risk category, they want to invest 3. It's going to be 8 combination 3. From the 7, from the moderate risk category, right there 7, and they're going to invest in 4 of them. So it's going to be times 7 combination 4. And then finally, right, on the low risk, there's 10, and they want to invest in 3. So it's going to be 10 combination 3. So 8 combination 3 will be 56. 7 combination 4 will give us what? 35. And 10 combination 3 will give us 120. If you multiply those out, it's going to give us 235,200. That's how many ways this can be done. And I believe, guys, that's it for this workshop. Let me take it back to your host, and they can tell you more good information for what's going to happen in the following weeks.
Thank you, Mr. Isasi, for a wonderful presentation. We want to remind you all that our previously recorded sessions are available on YouTube on the Tejano Virtual Events playlist. This session will also be available on the playlist later today. Also linked to this, we don't have the survey today, but we do want to tell you about the Tejano Virtual Event sessions. Before you leave, the first session at 1 p.m. today is Rio Grande Border Health Clinics. And for next week, the Math 13, 14, and 1324, we will be covering the final exam. Thank you all for coming in today. We hope that you have a lovely weekend. If you have any questions, please feel free to chat on the box or your mic. We hope to see everybody next week.